Okay, so we're past the abstract world of cyclic groups. We've been living there for a while. We've been calling them Z mod NZ. We've been calling them Z mod PZ times and all those. Let's get to something a bit more familiar to talk about subgroups. So on this slide, I've got a whole bunch of sets with their usual mathematical names. So my bold Z is the set of all integers. That is contained in bold Q, which is the set of all rational numbers. That set is contained in bold R, which is the set of all real numbers. And then the real numbers are contained in bold C, which is the set of complex numbers. So each of these are familiar number systems. Maybe not C so much, that's okay. But the other three, those should be pretty familiar at this point in our mathematical careers. And each one of these sets forms a group under addition, right? So I have some operation, here it's addition. I can take any two numbers in one of these sets, add them together, I'll still get a member of that set. Two integers combine to give me another integer. Two fractions combine to give me another fraction. Two real numbers combine to give me a real number. Two complex numbers combine to give me a complex number, right? And we have the identity element, which is going to be 0, and 0 is in all of these sets. And we have inverses in every one of these sets, right? Inverse of an integer is an integer, inverse of a rational is a rational, and so on. The interesting thing here is that all of these groups are nested inside of each other. Z's contained in the rationals are contained in the reals are contained in the complexes, and it's the same group operation the whole way through. The same addition that I would use up top in the complex numbers is the addition I'd use down here at the bottom for the integers, right? If I add two real numbers together, and both of them happen to be fractions, it's as though I'm just adding down here, down a rung on my ladder. So what we have is extra algebraic structure, right? If I'm solving some equation as real numbers, and I know that actually my x and my y are both integers, I can move to a smaller space and see if that makes my problem any easier to work with. So this idea of nesting subsets that are all groups, that's what it means to be a subgroup, and I'll have a formal definition on a future slide. If you want to get a little bit more weird with it, let's try not to get terribly weird. Here are some more sets. So I'm going to use the real numbers as my bottom rung of my ladder here. R bracket x is going to be the set of all polynomials with real coefficients, right? So anything that's like x squared minus 1, or 3x plus pi x squared minus 2, or maybe negative x to the power 407 plus 8, right? Those are all polynomials with real coefficients. They all belong to this set. R double brackets is going to be the set of all power series, again with real coefficients. So instead of just chopping off at some finite power, x to the 407, a power series can have powers of x of all degrees, right? It can have a constant term, an x to the 1, an x to the 2, an x to the 3, and so on without stopping. So you might have seen these in a calculus course when they talk about Taylor series. Now, every real number by itself you can treat as a polynomial that is just a constant term. So the real numbers are contained in R bracket x. And every polynomial you can think of as a power series that eventually stops. So every polynomial is actually a power series, right? So I can have R bracket x contained in R double bracket x, just as sets. Every element in here is in here is in here. What might not be obvious is that, in fact, all three of these sets are, again, groups, and they're groups under addition. So there is a 0 element in all of these, right? The number 0 is a real number. You can think of 0 also as being a polynomial that is just the constant term 0. And you can even think of it as a power series that is just the constant term 0 and no higher powers of x. And if you add any two elements from a single one of these sets together, you stay within that set. The sum of two real numbers is a real number. The sum of two real polynomials is another real polynomial. And the sum of two real power series is a power series. So this is just another example of nested subgroups, right? So R is a subgroup of R bracket X. R bracket X is a subgroup of R double bracket X. I'm not going to spend a whole lot of time on the algebraic structure. I personally like to work in Q double bracket X as a nice place for my research, but we're not going to talk about that right now. How can I find subgroups more generally, and what do they allow me to do in algebra? So in general, I need two sets, right? I've got some set H, and I've got some set G. H is a subset of G. Every element of H is contained in G. On top of that, G is going to be a group. I don't know what the operation is, so I'm back to using an asterisk or a star. That's my setup. I want to know, is H also a group under that same operation star? If so, that's what I mean when I say H is a subgroup of G. So every element of H belongs to G. H is a group with the same operation that G uses. That's what I'm looking for. As I've already been saying, subgroups are nice to work with because we already know how the operation works. So we already know how star works. On my previous slides, we already know how addition works, and it's the same kind of addition for every one of those groups, whether we're talking about integers or rational numbers or real numbers. The other nice thing about this restriction is that if we know that we are working inside of the subgroup, it makes it a lot easier to solve algebra problems. If I tell you to solve an algebra problem involving real numbers x and y, okay, there's a lot of things to worry about there. Are they roots of some polynomials, right? Do I have to perform some kind of quadratic formula to find out what they are? But if I already know that x and y are both rational numbers, then that means that x plus y must also be a rational number. And then I get extra things I can say about it. Right, that's kind of a generic statement. But group theory is kind of a generic subject. In general, how do I know that I have a subgroup, right? I said that the set of integers is a subgroup of the set of rational numbers when we are working in the operation of addition. Said that a couple slides ago. My definition says I need to make sure that H is a group under the same operation. So what do I need to check? What are my group axioms? Well, I need to have an operation, right? But that's already been given to me because I already said, say, that the set of rational numbers is a group under addition. And I already know that that operation plays nice with parentheses, right? It's associative just because G is already a group. There's only three things left to check. Number one, is the identity element in H? You always need an identity element in your group. Number two, do any two elements of H make another element of H, right? So I know that any two integers, those are both rational numbers, right? 2 is just 2 on 1, 7 is just 7 on 1. Add them up together, I'm going to get some fraction. But on top of that, I need to know, do they land back in my subgroup, right? Are they both integers in that case? Yes, they are. And finally, does every element of H have its inverse also in H, right? So there's just 3 things to check off my list. Do I have identity? Do I have closure, right? Do any 2 elements combine to give me an element of H? And do I have inverses still inside H? So let's take an example. If I'm running this checklist for a subgroup of the integers, so the integers are a group under addition. The identity element in addition is the number 0. So I claim that the set of even integers is also a group. Let me check my 3 properties. Is the set of even integers a group? Does it have identity? Well, 0 should be the identity element under addition, and 0 is an even integer. So yes, my set has identity. Is the set of even integers a group? Does it have group closure? Which is to say, is the sum of any 2 even numbers still even? Let me check with 3rd grade. Yes, yes it is. And finally, I need to make sure that my inverses are still inside of the subgroup. So what is the inverse for addition? I'm talking about negatives. Is it the case that the negative of an even integer is even? Okay, I'm up to 4th grade now, and 4th grade is telling me, yes, the negative of an even integer is still even. So we've satisfied all the properties of a group. The even integers are going to form a group because they are contained in the set of all integers, and they use the same plus sign as all ordinary integers do. Then the set of even integers actually forms a subgroup of Z. Now it's handy to have a set name for this group, so I will call it 2 times Z. Right? A lot of talking on this slide. In general, if I'm looking at all the multiples of some integer capital N, I'm going to give that a set name of capital N times bold Z. And what I mean here is just look at the set of all multiples n times a, where n is my fixed integer I picked up here, and a can be any possible integer, right? So this set nz is all integer multiples of n, and in fact, this will always be a subgroup of the integers z. Right? So 0 is always in here. I can add in here and always factor out that n. I can take differences and find my inverse elements that way. It's all great. So this subgroup nz, you might recognize this notation. I've already been sneakily using this notation when I talk about the modular arithmetic, z mod nz, right? That is the same thing going on here and here. There's some curious business going on with my quotient symbol there, right? I will not talk about this today, because I feel we've already talked about a lot, but maybe you can figure out what is going on in this notation and how we could apply it to other kinds of groups. Okay, enough teasing. At the beginning of this lecture, I talked about cyclic groups, and I said that brackets A is a cyclic group. In general, This will work for any possible group. Let's say that G is a group and A is an element of G. I'm going to take brackets A to be a set whose elements are all possible combinations of A and A inverse. So in a cyclic group, my brackets A is equal to the entire group G. That doesn't always happen. That is a special property of cyclic groups. But in general, this gives us another example of subgroups. So what is 2z, right? That's all combinations of the integer 2 and the integer minus 2. So 2z is one of these generated subgroups. And so is 3z, and so is 4z, and so is 5z. You can do that in any group that you want with any element that you want. A nice thing about these generated subgroups is that the number of elements in them is exactly equal to the order of A. So we've looped around to the beginning of this lecture. So for my integers, right, if the even integers are generated by the integer 2, there are infinitely many of them because 2 has infinite order in the set of integers. Let me finally close this lecture with an example of a set that is not a subgroup. So we've seen an example of subgroups in the integers. We've seen examples of subgroups generated by particular elements. Let's look at the set of irrational numbers, which is of course contained inside of the set of real numbers. The real numbers form a group under addition, but I claim that the irrationals don't, and they fail that on two, I claim that they don't form a group, and they fail my test on two different counts. So number one, I would ask, do the irrational numbers form a group? Do they have identity elements? Well, no. My operation is addition. And my identity element for addition is the number 0. But 0 is a rational number, not an irrational number. So 0 is not in the set where I need it to be. Since the irrationals don't have an identity element, they automatically, categorically cannot be a group under addition. Let me try, just for laughs, to see if the irrationals are closed under addition. So here is an irrational number. It's the golden ratio phi. Here is another irrational number. This is sometimes called the small golden ratio, or the algebraic conjugate of the golden ratio. None of that vocabulary matters. But when I add them up together, I can see that these fractions have the same denominator. My root 5 and my negative root 5 are going to cancel, and that gets me to 1. So some combinations of irrational numbers give me rational numbers. They land outside the set of irrational numbers. And once again, that is not allowed for a group. If I combine two group elements, I am supposed to stay inside of that group. These naughty irrational numbers have broken out. They're free. So on two counts, the set of irrational numbers is not a group. All right. So this lecture had a lot of definitions in it. I will try to have some concrete examples at the beginning of tomorrow's lecture, where we can work with these definitions and put them to use in some algebra problems. All right. Thanks for sticking with it.